continue. So last time we left on latent variable models. So uh, yeah, so just a quick go through. We initially completed. 1 second. Um, yeah, so we initially finished maximum likelihood, MAP estimate, and full Bayesian inference, and now we are and then we gone through an example of that, and then we started with latent variable models. So last time we discussed how introducing a latent variable makes sense in making many decisions even in our day-to-day life. And so yeah, uh, in so, yeah. So our basic walkthrough of latent variable models is from all of the x we determine uh, 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 some latent variable z that was the cause of all the x, and we would try to predict y directly from z. And then we just started off with the GMM of Gaussian mixture models, where you where our aim is to determine from which Gaussians the data that we see come from. It's a clustering method. It's a soft clustering method where each data point has each data point has a probability of it belonging to this cluster A, cluster B, or cluster C when we are doing Gaussian mixture model for three Gaussians. So in that we had seen earlier that the total parameters that we would want to estimate are simply uh, let's say we are just focusing on three Gaussians, then pi 1, pi 2, pi 3. Uh, this just says that from which Gaussian the yeah from yeah from which Gaussian the data point comes from. Pi 1 is the probability of it coming from Gaussian 1, and so on. So yeah, this is kind of a latent distribution where so in any of the latent variable models that we'll study, there is some kind of generative story assigned to it, which says how the data point came to be. Uh, so uh, yeah, so here let's say yeah, here we are assuming Z is this categorical distribution that says from which Gaussian it comes. Yeah, pi 1 being the probability it came from Gaussian 1. And then Z2x is the conditional probability that, let's say I know that it came from Gaussian 1. What is the probability of me seeing that, knowing that it came from this Gaussian? So here P of Z is categorical distribution, and probability of x given Z is Gaussian. So yeah, and each Gaussian will have new and covariance matrix, these parameters with each Gaussian. So at the end, we are left with estimating this. So yeah, at the end, we are left with this all of these parameters, pi, nu, and covariance matrix for each of the Gaussians. So we know this pi, all of the pi's are just scalars that just tells us probability of which Gaussians. All the news are vectors. Let's say if we are dealing with n-dimensional data, then each nu would be n-dimensional vector, and each of the sigma would be a n cross n covariance matrix. So in yeah, and then these are the constraints that we need to take care of while yeah, while obtaining these parameters that since pi is a distribution that says yeah, that gives probability of each of the Gaussians the sum of pi. uh, since it's a discrete distribution, sum of pi should go to 1, each pi should be positive. And here when I say pi obviously is a variable, and then yeah, uh, just symbol pi, yeah. And then sigma is yeah, since it's a covariance matrix, it's a positive semi-definite, and it also should be symmetric. These are some of the constraints that we need to take care of. And what do you generally like to do is maximize the likelihood for these parameters and get, okay, I've seen this data, which are the best parameters that explain my, I already know all the distributions. I just need the parameters of this distribution and which value provides the maximum likelihood of the data that I've already seen. So, yeah, this is a simply a Gaussian mixture model. And now yeah, and then today's lecture will try to do EM algorithm and explain Gaussian mixture model with it. Uh, just Swapnil, I wanted to ask, like today, how much time do we have?
Up till 10:15, and then 10-15 minutes of questions.
Okay, sure. All right.
So it's 8:48 right now, so roughly 1.5 hours.
Yep. Okay. Yeah. So we'll start with first estimating how. Yeah. So Gaussian mixture models. We have C different clusters. And when I say, okay, C clusters, so now we have, yeah, pi 1 to pi. These are the variables that are associated with telling the probability which cluster it came from. And then with each cluster, we have a Gaussian associated. So yeah, we are interested in these quantities. So let's formally define what each of these is. So X is our data that is given to us and that we inherently want to cluster. Let's say T is a latent variable. So now this is not given to us. This is something that yeah, we are simply given X data and that's it. Nothing else is given to us. And T is some latent variable that we are inherently defining because we are trying to fit a Gaussian mixture model to our data. And in Gaussian mixture model, we are assuming that the data points that we see have come from C different types of Gaussians. So this is our modeling assumption, and yeah, and this tells us which Gaussian data came from. In GMM, we have T as a discrete random variable, and it takes up values from 1 to C. So yeah, if T is 1, then we know that the Gaussian came from, sorry, the data point came from first Gaussian. So simply the distribution that we have over C is this, over our random variable is this. So yeah, it's a categorical distribution, discrete for, and for all the C's, we need this to be 1. So, so we have our prior distribution defined. We don't know this random values pi 1, pi 2, pi 3, but yeah, we have our prior distribution defined for us. And then let's say now, so in generally in all the in all the theory that we'll go through in latent variable models, uh, P of T and P of X given T are modeling assumptions. Uh, yeah, these two I would say are the main modeling assumptions that we would always make. So this is something that will always be like not given to us, but it's something that we'll impose and we'll know already. because choosing P of t and choosing P of x of t dictates our model. And yeah, so in Gaussian mixture model, we have this P of t as a categorical distribution and P of x given t as a Gaussian. So since we are fitting a Gaussian mixture model, it comes from the definition of exactly what we are trying to do. Uh, a distribution over your latent variables, and then how you see x from it. So it's generally you first select t. From t, now once you know t, and then you'll get, okay, now what's the probability of seeing the x's? And then now this is just a Gaussian. And nu of I and sigma I are the values that are, okay, I would rather, yeah. So ti is equals to c indicates that, okay, this then yeah, this latent variable, if it takes the value c, that indicates it came from cth cluster, and the nu of c and sigma of c are the parameters of the Gaussian, of cth Gaussian. This is indicates cth Gaussian. And if we say, if the data that we see is x, these are the n data points that are given to us. For each data point, we'll assume that yeah, we have a different t1, t2, which says, okay, from which Gaussian is that particular data point coming from. So this is our kind of a probabilistic graphical model, that this is a latent variable, and this is a seen variable. And I'm indexing by I to indicate, okay, yeah, so just notation that I'll use, t is a random variable. Indexing by I indicates I'm indexing for the ith data point. I'll also sometimes index by C, which would be, yeah, for cth cluster, and capital C is just total number of clusters. So now up now we have set our priors. So prior is P of Ti is equals to C by C, and our posterior is Ti is equals to C. This is what defines our Gaussian mixture model right now. X is given, and this is modeling assumptions. So yeah, so given these two values, let's get the probability of X. So we know we can simply do marginalization over all the latent variable, and this is some uh, you would frequently observe this. And uh, now since we know t is over all the t's, and this is because we know t is a discrete variable in Gaussian mixture model at least, but generally if t is a discrete, there would be summation, and if it's a continuous, then we would integrate over it. Then this is simply this. And the all the possible values that t can take is 1 to c. We saw that. So mm, I should use another variable here. Um, yeah, T is a random variable and these are the values that it can take. So yeah, I'll just subscript it by small c. So this would be, yeah. So and we know P of t given c is just for Gaussian mixture model, this would come out to be P of t is equals to c simply pi c, and probability of x given t is equals to c we know as, so this is the probability of yeah, P of x. And now what we would want to do is get its likelihood. So yeah, so now in order to do just likelihood as we have seen before, what we would simply do is this we would if if I'm indexing it by xi, say, then all of this would be indexed by xi, and then we would take this yeah, we would take product of all of these probabilities, and then we would take just simply the log of it. So uh, yeah, I'm not doing that here, but you know how we would calculate the likelihood of this. So any doubts still here? Okay. So the values that, so while you're doing the EM, we'll see that this thing, the formula of likelihood, it's difficult to maximize over it. Uh, and intuitively, the results come out to be like, now, okay, first of all, now what we want is that just given this xi values, we want the estimate for pi c, nu c, and yeah, nu is the mean, and covariance matrix of yeah, index by c. So, and this is the data that we want for all the clusters, and so the formula that come out to be is, and this is quite intuitive, all of this. And now I'm summing over all the data points. Just writing down the formula. Yeah. So this is that. Yeah, we know this thing is a Gaussian. So this, oh no, this thing is not a Gaussian. Probability of x given ti. So I'll write what this thing is, but okay, okay. Your p of ti is equals to c given xi would simply be probability of yeah, xi given t times probability of t is equals to c divided by probability of xi. Simple base rule, and we know each of these quantities. So probability of ti is equals to c is simply pi c. This is nothing but a Gaussian. And this denominator is something that we just calculated here. This is summation of all of our classes. And so this c and this c's are different. So let's just say this is c dash. And this is the probability of yeah, basically posterior, but yeah, given xi, the latent variable that that data point came from. And so, and now if you substitute this thing over here, then you would get the probability of, yeah, for Cth Gaussian. Uh, so, so generally this, yeah, uh, this tells us now I have my data point xi. What is the probability that it came from my Cth latent variable? So, like the probability that it came from not Cth latent variable, a latent variable that took its value as C. And so this is basically the weight that the data point is contributing uh, for determining the Cth Gaussian. So I'll go to each of my data point and ask, okay, uh, how much do you think you belong to the Cth cluster? And that is nothing but given the data point, yeah, probability of uh, latent variable that generated it being C, and then the data point came to be. So yeah, I hope you are getting this. So now I have this data point, and the probability that it came from Cth latent variable is how much it's contributing to the Cth Gaussian. So it's just taking all of these xi's and yeah, a weighted average of all of yeah, how much each of this point is contributing. And similarly, let's say yeah, in 1D case, then the variance is also calculated similarly. Yeah, so again, this is also weighted average, and this yeah, probability of Ti is equals to C given Xi just tells us uh, yeah, as explained earlier, seeing that data point, how much do you think it came from Cth Gaussian? So what we would kind of iteratively do in this is, and yeah, okay, so now we have nu of C, we have sigma square of C, we still need pi of C. Pi of C is simply, so yeah, go to all the data points, and so pi of C is kind of probability of yeah, so your random variable taking the Cth value, so you just go to all the points and basically see how much of that point belongs to the Cth quotient. So that tells you that while yeah, so from all the points, you know, okay, this point is, let's say, uh, let's say we have just three data points. Mhm. And pi of 1 for these three data points is this. So so it's simply first point, the probability of first point being generated from first Gaussian is 1/3, and then you just add all of these up, 1/3 plus 1/4 plus 1/4, and you kind of normalize it by dividing it by 3. So uh, now you know that all like you know how each point yeah, how much every point belongs to this first quotient, and then now whenever you want to generate something from the first quotient, now let's say if all the points belong to first quotient, each of them just give 1 1 1 1 1. So it's like, okay, everything completely belongs to first quotient. So our pi of 1 would simply be n by n, which would be just 1. And so whenever you need to generate some new data, let say, so pi of 1 tells you, so whenever you need to generate new data, we saw first you would query this t of pi, pi 1, pi 2. sample from this, and let's say if we sample pi of 2, then we would sample our x from this. So, but if everything was already from the, let's say, first Gaussian, then the probability of pi of 1 is equals to 1. And then it says simply that since every data point just came from the first Gaussian, you always, while even generating new data, just samples from the first Gaussian. So, yeah, so the entire data, the entire generative story, this pi of c tells you, okay, if you want to generate new data, how you would sample from your latent variable. So these are the formulas of formulae of how, yeah, in Gaussian mixture models, if let's say you would have new data, then you would kind of, yeah, you would find new c, you would find sigma square c, you would have all your Gaussians, and you would also have pi c, and then you would kind of iteratively change this pi c. So yeah, first let's say if you first let's say if you find pi c for all of your participation for all of your data, then you would, using this pi c, you would find nu c and sigma square c. But you see when uh, yeah, when you have your new means and your new standard deviation, your normal distribution itself changed. So again, you will update your this pi c, the probabilities of your latent variable, and it's an iterative yeah. Uh, so it's iteratively you would update your pi, and iteratively you would update your nu and sigma. So yeah, and this is simply what we would do in EM algorithm. So in EM algorithm, updating your pi would be your E step, and updating your nu and sigma would be your M step. So E is expectation step and M is maximization step. We'll look into it further. But so this formula would come from EM algorithm, but uh, even if it, yeah, but intuitively it makes sense. Okay, this is the right thing to do. So let's just now start with. So any doubts still here? Anything? So are you guys understanding what I'm saying, or should I slow down, or should I increase my pace?
Might be easier to ask someone to review, like, very briefly what they understood from this.
Yeah.
Any
Anyone?
volunteers?
Yeah.
I can go first if it's okay.
Sure.
Right, okay, so basically we're trying to fit a Gaussian mixture model. So in this case, we have got 3 Gaussian, and we are trying to find, we're basically trying to cluster using these 3 Gaussian, but we don't know what is the probability where this Gaussian actually, like, what was the probability that this data point belongs to this particular Gaussian. So pi is the probability that would tell us, okay, this belongs to this this cluster, and pi is one of the parameter that we're trying to estimate. So because we're doing a soft clustering, we don't have a definite answer where we know that this data point definitely belongs to this cluster, but here we get a probability distribution, and based on the probability distribution, we know which data point which cluster it's belong to. So in this case, so we got this parameter pi, and based on like how many cluster we got, if in, for example, C is 3, then we would have like pi 1, pi 2, pi 3, and then we would have these other parameter, because this is a Gaussian mixture model, so we would have these parameter mu and sigma, the mu and covariance matrix. So in the M step, we trying to calculate the probability values of like basically we're trying to calculate the pi, and in the M step, we're trying to calculate the sigma and the covariance matrix.
Sure.
So, yeah.
Yeah. Nice. So she summed it up nicely. And now, so for expectation
Just
max,
just one point. Instead of writing or saying calculate all the time, try to use estimate, because none of this is perfect. It's all driving towards a convergence point,
yeah,
but that's still like an estimation procedure.
true.
Right, okay, that makes sense. Thanks.
Sure.
So yeah, so now let's start with the expectation maximization. So I kind of first hold up on this and just revisit Jensen's inequality first. So if you are all familiar with it, just like maybe give a thumbs up or something, that then maybe I'll just skip it. But if you want me to revisit it, then even that's fine. Show of hands, thumbs up, unmute yourself. Should I go over it? Should I just skip it?
I mean, what I remember from about Jensen inequality, it's basically if we take function of expected value, that would be greater than it's always greater than equal to the expected value of the function.
Provided the function is a concave function.
Yeah, okay, yeah, if it's a concave function, yeah, that's right. But if you want to go over it, it's fine. I mean, if you want to go through the derivation, that would be good.
Okay, yeah. So okay, I'll provide the derivation then. So now yeah, I hope first of you are all familiar with the definition of a concave function. So let's say if this is some concave function, and now the reason that we uh, so this logarithm is a concave function, and that's why the Jensen's equality is like very useful in all of our mathematics in this yeah in EM algorithm, because log is a concave function, and so we can use the Jensen equality here. So let's say if, this is some concave function. Yep, so Jensen's equality simply says that if this is some line, then yeah, you can get any point on this line if you remember the parametric equation of that line. Then we would have yeah, let's say if we go alpha in this direction, then this point would be alpha a plus 1 minus alpha times b. And then so yeah, and so if we are kind of interpolating between this and this point, so this point is alpha a plus 1 minus alpha times b. And if it's a concave function, then this point would be alpha times f of a plus 1 minus alpha times f of p. And if it's a concave function, that it simply says that the value at this point, corresponding value, would always be greater than just yeah than the value over the line which connects them. So it's f of alpha times f of a plus 1 minus alpha. So the value of function on this point is this. So it's simply alpha a plus 1 minus alpha times p. And this is always greater than equal to uh, yeah equal to just a value on the line that's connecting the 2 points. This is the so this is yeah, so if f is a concave function, then this always holds. And so yeah, alpha is between 0 and yeah, this is kind of a this is Jensen's inequality, but Jensen's equality is more generalized. So now yeah, here we are simply having this alpha 1 and 1 minus alpha. We can we can introduce more variables, and yeah, it's just simply linear interpolation. So this is so yeah, again, here in this case we need to ensure summation of alpha I. So you can easily prove this using induction. Uh, just take first yeah uh, first take this alpha 1 and keep all the yeah alpha 2 to alpha n aside. So this is equal to alpha 1 e1 plus 1 minus alpha 1 e2. No, sorry. 1 minus yeah, and then you so first just using this, now your a is simply a1 and b is this entire summation, and then you can yeah, you can just simply linearly inductively you can just take alpha 1 aside, alpha 2 aside from this, and then you can easily prove this. Here instead of just a and b, now you have a1, a2, a3, a n distinct points, and then you are, if it's a concave function, so uh, it's in 3D. Yeah, let's say this is a1, this is a2, this is a3, and this is a curved surface, and then you are kind of yeah, you are choosing this points, and then since it's a concave function, the and if we are just linearly changing each of this variable, then we will get a plane connecting all of this. And if it's yeah, I hope you are able to visualize this. There is this plane, but this the concave function is over this plane, and then so yeah, any value over that concave function would be greater than the corresponding value that is inside the plane. Yeah, it's kind of by the definition of concavity that yeah. So so this this is a general form of Johnson's inequality, and in the discrete case, and then this is like easy to prove in the discrete case, and here I'm kind of cheated off a bit by proving this in the discrete case, but a truly general thing would be to prove it in a continuous case, which we would use in many times. But proving that is hard, because now instead of, you just don't need to sum over alpha I is equals to 1, but you need alpha I such that they integrate over to 1 in your space. So that is a constraint. And yeah, but it's yeah, you can kind of visualize, and there are like make alpha I so small that it's kind of d alpha I, and just taking such small parts, and then just summing over it is just integrating over all those small values of alpha I. And now if so your alpha I has just this one constraint, and in most of these cases the alpha I that comes out to be is probability of seeing the data point ai, and it satisfies this constraint, then so we would simply have, this would simply become the expectation of ai, and that's what Deb mentioned. This would just become expectation of a, and a is a random variable and ai are those realizations. Then this would simply become expectation of f of a. So I hope you are familiar with Lotus, and it simply says that yeah. So I hope you're familiar with Lotus, and that's why this translates to this. That's why this and these are the same thing. Uh, so ideally, what you would want is not alpha here, but if alpha is the probability of f of ai, but Lotus simply says that you can unconsciously just replace f of instead of probability of f of ai, you can just replace it with probability of ai, and that's just alpha I. So yeah, so any doubts in this? So this is this form of Jensen's inequalities we are going to use, but all of this is just simply Jensen's inequality. This is Jensen's inequality. This is Jensen's inequality. This is Jensen's inequality. And yeah, so that's the thing. I proved this statement only for the discrete case, but it also holds true for the continuous case, which I haven't proved, and uh, frankly, I do not even know the proof of that. But it's yeah, simply instead of summation, you would have integration over, and alpha I would be a PDF instead of PDF of AI. Yes, simply just the definition of expected value of your random variable. So yeah, for discrete case you can easily prove that, but yeah, for continuous case, no. So any doubts in Jensen's inequality? And then the yeah, so in previous lecture I had mentioned that KL divergence is always positive, but you can also prove this using Jensen's inequality. So I'll just quickly go through in that as well. And then it all everything connects. Like you can prove KL divergence is positive, and then this would consequently lead to us showing that mhm, where was it? That the difference between the entropies, that cross entropy and entropy. So the difference between them is simply KL divergence, as we saw earlier. And so yeah, HPQ and mine, yeah, HPQ is cross entropy term, H of P is the entropy term, uh, and if you subtract them, then you just get the KL divergence. And if we show that KL divergence is positive, then we also show that this thing is greater than zero, and which would show that so cross entropy would always be greater than entropy. So yeah, and we know h of p is simply the entropy. So if you are in information theory, if your latent distribution comes from sorry, not latent distribution, if your distribution comes from p and you are estimating it with q, the entropy would always go higher if as q varies between p. So if uh, so if you are kind of bringing down h of q, the maximum it can go down is to h of p. So simply if you are minimizing with respect to q h of p comma q, then you will always end up with q is equals to p. So because the lower bound is set. So yeah, so you can prove all of this with Jensen's inequality. So yeah, so we know KL divergence between two distributions q and p is again I'll use Lotus here, and then yeah, you can see these and these are the same thing, right? So x is coming from q of x, and this is the function. So hmm, and now if we so simply and now see, okay, this since we have a logarithm function, we'll use we can use Jensen's inequality. F is concave here. Uh, so yeah, because this function is concave, we have logarithm here. We'll be able to use Jensen's inequality, and then we would have um, so yeah, expectation. It's yeah, the sign is just flipped because I substituted this part here, and then this would be equal to log of expectation of x is coming from q of x. So this would simply become log of integral of q of x, p of x, q of x dx, which equals this and this cancels out, integration of p of x dx, which is 1. So now we know the expected value of x given q of x is less than this thing evaluates to 0, and hence this term is less than 0. And now if you just multiply -1 by both sides, then we would get negative of this expectation is greater than 0, and that is simply the KL divergence. So you you prove that KL divergence is always greater than 0. And so now we have proved KL divergence is greater than 0, and hence gross entropy is always greater than entropy. So yeah, so any doubts in this proof, and we'll use, I went through Jensen's inequality because we'll use it in the expectation step, in expectation maximization. But yeah, any doubts, feel free to post it on chat if you have any. So now let's do generalized expectation maximization algorithm where yeah. So now we have again same notational conventions. T would be our latent variable. X is the scene data, observed variable. Latent, observed. Yeah. So so in GMM we had and as always you would always have P of x given T and P of T. So and we'll again if we are interested in finding P of x, then we would simply marginalize it. So in discrete case, yeah. So now let's say again in discrete case our latent variable T would take discrete values, and just to keep it consistent, let that be indexed by C. But here C does not necessarily mean the cluster. C can be anything. Yeah, C are just those discrete values that our random variable T takes. Let's say for ith data point. And in GMM, we had this distributions, but we are just doing a generalized TM. So yeah, this is provided, and this is provided. Now, as I mentioned earlier, our goal is simply to maximize the likelihood in order to estimate the parameter. Okay, so what are we essentially doing here is we are interested in finding. I would uh, subscript this by theta. Yeah, so we are interested in finding this parameters theta of our distribution that yeah, that dictates how xi came to be. So in previous example in GMM particularly, this theta would have been nu and sigma. So yeah, let's just maximize the likelihood of our parameters theta given x. We know that simply product of xi. So like theta subscript just indicates that that distribution is parameterized by weights theta. No, by parameter theta. So yeah, we are simply interested in, so as we know the definition of likelihood, we would go to each data point and see, okay, what's the probability that I have these parameters theta and what's the probability that it came from the distribution with those parameters. So I hope this doesn't further need any explaining. So yeah, we are interested in maximizing this, but as again, we would use a log likelihood trick, and maximizing this would be same as maximizing the log of likelihood, and then this would become um, summation. And we saw we know p theta of xi is this, so this becomes maximizing theta. Again, now when I'm writing summation, please bear in mind I'm doing it for discrete case, but it shouldn't necessarily be the case if t can be a continuous random latent variable, and if that is the case, we would do integration here. So you can also write this simply as this. So yeah, this is equal to. So maximizing this quantity is a bit hard. So why you would say that? So first of all, you can always like plug it into your gradient descent or any of the optimization algorithm, but there are always a few constraints that you need to keep in mind. So you are maximizing over theta, and theta cannot just always take some random values. As we saw earlier in GMM case, we need like if a theta can be a covariance matrix and it needs to be positive semi-definite, it needs to be symmetric. If we have some distribution pi, then you need to ensure that it sums over the summation of over all of them is equal to one, each of them is positive. So in most of these optimization problems, you would have all of this set of constraints. So you can theoretically put into gradient descent or any of the optimization algorithms and just find your theta. But what EM algorithm does this trick is, instead of yeah, uh, so otherwise, if you don't do that, then because you have this summation of log of summation, the procedure of obtaining the most optimal value for theta becomes difficult. And now again, because it's a favorite logarithm function which is concave, and we can now easily use this Jensen's inequality, we would kind of lower bound this function. And this is the trick that in most of the Bayesian theory we would use, and in many other optimizations. If I want to optimize this function, and so okay, so there are these two functions, function A and function B, and this function B is always the lower bound of my higher function A. So now if I want to optimize this thing, if I'm optimizing the upper thing, what I'm basically doing is pushing down, and I know since this thing is always going to be less than this, even this thing gets pushed down. So, I hope you are able to make it, the connection. So so and this is kind of minimization, but again, in maximization we have this lower bound, and if we are pushing this up, if we are always maintaining that this function is always going to be greater than this, then maximizing the lower bound forces this thing also to get maximized, because as this thing increases, the function A always has to increase, because function A always needs to be greater than this function B. So increasing function B yields to increasing function. So this kind of basically pushes function A to go up, but now we are dealing, yeah, but because optimizing function A is quite difficult for us, we are optimizing function B, which is lower bound. So in the analogy, this would be function A, and yeah, optimizing this is difficult. And but since we have this uh, nice little thing of uh, lower bound, we would instead find lower bound of this entire quantity. And this is called variational lower bound, evidence lower bound, ELPO. These are the terminologies that you find in most of the literature. What this term is, we'll go through it in a bit. But yeah, so it's simply this, like applying Jensen's inequality to this entire thing. So if you are able to make the connection, uh, okay. So first, let me introduce. Yeah. So now let's say you have, this is your theta. This is a function. This is the thing that we are interested in. Let's say this is our lower bound. So yeah, again, notational convenience, L of theta is our lower bound of P of X parameterized by theta. So if this is the lower bound, then sometimes there is a possibility, okay, that this lower bound is kind of gets stuck local minima sorts of thing. So yeah, so optimizing this low, so okay, you can see this lower bound is always less than P of X. So this is all evidence. So we know this is always less, but optimizing this would yield us a local minimum instead of a local maximum that we are interested in. So instead of just considering one lower bound, what we would do instead is consider a family of lower bounds. So why just stop at this? We would, but obviously all of these lower bounds should be less than p theta, less than our evidence, because it's a lower bound on all of that. So instead, now we would use a family of such. These are all, so instead of one, yeah, instead of this one lower bound, we have now instead family of lower bounds. So the way we would do is we would uh, include an additional free parameter that we can change, and every time we change it, we would get a new lower bound, and then we would optimize over op- yeah, we would make our optimization over finding such a lower bound that gives us the maximum value. So are you all here with me? So Any doubts still here? Okay. So instead of just maximizing one lower bound, we are now considering family of lower bounds. So this was our original equation, and we would now introduce a new free parameter, which is yeah. Let's just the thing that we introduced. So I'm just multiplying this equation in numerator and denominator with u of ti is equals to c. Then this thing. So these and these things both are the same. This and just multiplied and divided by this q of ti is equals to c. And now that allows me to get a lower bound because now just remember that q of ti is equals to c is so yeah is in this case a discrete distribution because it yeah it provides for each ti we have yeah because ti is a discrete variable is defined over ti, it's a discrete distribution. So now I'm just simply applying Jensen's inequality here. This forms my alpha and this thing forms my a. Remember it. Yeah, summation of alpha ai is greater than summation of alpha I function of a. Now using we would have summation of I is equals to 1 to n. So log is our function here, and again, since it's concave, we would have c is equals to 1 to c dash. Alpha I would come outside, and then function of all ai's. So this is our lower bound for the discrete case. And now we have this additional free parameter of q, which dictates our so q of ti again. It needs to ensure this. It's simply a distribution. It needs to ensure the summation of over all the values that c takes needs to be one as we saw in Jensen's inequality. So it's yeah, it's a variation. It's called a variational distribution, and it's kind of a we would vary it and changing q of ti. So in this optimization, we saw the q of ti never came into place. It's just a free parameter that we introduced, free function kind of that we introduced, and then changing that would yield as different evidence lower bounds, and then we would have a family of lower bounds, and then we would optimize over q, which would give us yeah. So we'll see how that looks like, but so so I elbow this L of, and now so what we changed from L of theta, now we have L of q of theta because we introduced this new additional free parameter q that so this was elbow, this is family of lower bounds. So this L of theta is not called elbow, sorry for that. This the entire family of lower bounds is called evidence lower bound or variation lower bound. Variational just because we are able to vary this different distribution q. This is just lower bound. So now we have elbow is L of q of theta, and we are able to vary this distribution q and then obtain different lower bounds. And now we'll be optimizing this over q of t. And now again, yeah, so instead of instead of maximizing our lower bounds, what we would sorry, instead of maximizing our evidence, we would instead maximize this elbow. And like this is something common in Bayesian theory that you would also see in variational inference, variational autoencoders. Instead of just as explained earlier, we are now optimizing, maximizing this lower bound in order to push p of x as up as possible. So, huh. So and then E step is E and M step are simply kind of the maximizing this. So, E step would be maximizing this with respect to Q and M step. I'll go through the details, but just to get the taste, and M step would be maximizing this over theta. Just working on this evidence lower bound. So yeah, maximizing over Q would, and in each step we would keep theta as constant, and in M step we would keep Q as constant. So yeah, let's just see what happens if we keep theta as constant. So we have this distribution P of x. We have this. All of these are different lower bounds for, let's say this is for Q1, this is for Q2, this is for Q5, and so on. So let's just fixate some theta. If we keep this theta as constant, and now we'll have multiple distributions, we would choose the Q that would yield us the maximum value of P of x. Sorry, so these are different. So each of the lower bounds will have some value, and we would choose the Q that would give maximum value at this theta. So it would be kind of this one. Let's say this is slightly bigger than L of Q1. So in this step, we would just choose this Q. And all of these will have some value on theta, but we would choose, yeah. So our choice of Q would be such that, and always remember that Q is a distribution. Q of Ti is equals to C that has this property, and that's just yeah. So because Ti is discrete in this case, Q is a discrete categorical distribution. And we would choose this maximum value over the evidence lower bound. And then once we have this Q, we would kind of fixate it and then move our parameter theta by optimizing this. So now this is our evidence lower bound. And now what we would do is kind of move this to this. Now the theta becomes a free parameter that we are changing, and theta is again the free parameter, and we are maximizing over that. Anything, and this is our lower bound. So since we are maximizing, now we have this theta. So initially this, let's say this was theta k, then in the next iteration we increase theta k plus 1 to this point. Now we would fix it again this theta. So this would be M step. So in each step we would choose our Q. In M step we would change our theta. We would get a new theta k plus 1, and then we would fixate in the next E step again. We would fixate this theta. We would again have some new family of distributions. And for this theta, we would choose the distribution this value of theta out of all the different q's, we would choose again, which would give us the maximum value in this point. That would be this. And in that case, so the thing it would eventually converge is to the local maximum. So now let's say we got this theta. So this now in the second m step, now we would this quantity over here over theta, and then this would converge to here. And eventually, what we would end up is at this point. So my drawing was not the best, but I hope this picture is clear of how. So this was all like theta is just 1D variable, which would never be the case. But just for the visualization purpose, were you able to understand the diagram? How in each E and M step we are changing the theta and Q? Any questions?
I've got one question. So
Yeah.
how many lower bound are we introducing here? Like, is it like, because I remember you, I think in one of the equation, you multiplied and divided by qt. I think that was the step when we are introducing lower bound, right? Like a family of lower bound.
Yeah. So initially we just had so we are introducing a free parameter that we are allowed to change, and then so that's kind of okay. This is like so q of ti is some free. I'm saying free parameter, but it's not a free parameter. But I'll clear it afterwards. But okay, let's consider uh, q of I as just some free parameter that we are allowed to change. Uh, let's say take some value from yeah. So for each q of ti, we would have some lower bound, and yeah, and because it's simply a free parameter that we introduce by multiplying and dividing, and we just need to keep in mind that okay, sorry, where did it go? Mm, yeah, we just need to keep in mind this constraint where summation of q of ti is equal to 1, and then it's just simply math. This q of ti is something free that we introduced, we can reuse it, and yeah, every time we change this, we would get this new lower bound. uh, did that answer your question? So
Yes.
there are not so there are not this discrete number that we are choosing. Okay, let's say we are optimizing over 10 lower bounds or 15. It's just a family of lower bounds. Yeah, every time we change a particular value of q, we would get that. And so this each step is very so yeah. So but any doubts in the diagram? Was the diagram clear to you, everyone? How in so are you able to first visualize intuitively why maximizing the lower bound is like getting us what we actually need, uh, a local optimum of this p of x that we are interested in, and how smartly we are moving from each of this first iteratively moving from optimizing over q, then optimizing over theta, optimizing over q, and optimizing over theta. So any doubts in this diagram? Should I go over through it again? If you don't understand, I would be happy to. Just maybe indicate something in chat or show a thumbs up or unmute yourself.
Fenil,
Hmm?
like, say the distribution that we are introducing is just the approximate distribution that we are assuming to the true distribution, like in a way, right? Well, it is similar to variational Bayes inference and like that way. So in that case, we introduce a distribution that is going to be most likely to the true distribution in a sense, or like sort of a latent variable that leads to some true distribution.
So when you say true distribution over what?
Like basically true distribution over the particular data points that we have right now, like the cluster, basically, let's say.
No, no. So
So
this latent distribution is defined over our latent variables, q of
yeah,
t.
like this latent variable defines that data points that like basically defines a true distribution in a way, right? Means like there is some process that like basically pass latent variables, it generates some data, and that data is say belonging to the true distribution, like, right? Or is it something different?
So yeah, means like in the E step you would see that this thing that we want actually like so it's same as this posterior distribution that we are but at the end our goal is to obtain this p of x and nothing else. And q of ti is currently simply a free parameter that we have introduced. Here we are not trying we are not enforcing any constraint that it needs to be similar to this or anything. It's just a free parameter that you can think that we have introduced. And so now instead of considering a single lower bound as we saw, which would come which might end up at local minimum, we are considering a single lower bound that can end up at I hope that answers your question. And then in the proof that you would see that
Can
this
you
q
repeat a bit? Like I think your audio got lost in between.
sorry, yeah. So currently we have made no assumptions. We are not trying to make q similar to anything. We have just introduced q to to be
Did we
yes.
lose him or is it just me?
No, like it's the same for me as well.
Hello, I can hear you.
Oh, okay. Sorry, my bad.
Oh, so
No, yeah, like
you can
your
hear me
screen
now?
got yeah, yeah. Now I can hear you.
Okay, nice. So currently the q that we introduced, you are not enforcing any constraints here that q needs to be similar to something or anything. Q currently the way we introduced it is just multiplying and dividing by q, and it's just allowing us a free parameter to consider a family of lower bounds instead of just a single lower bound. So so just q is currently just a free controllable parameter that we would change uh, to get family of lower bounds, like the way we have introduced it currently. So does that answer your question?
Okay. So means in this case, Q does not depend on the actual data, like or something like that, where latent variable generating the data.
No, currently, so we will be optimizing over q, and then but our aim right now is to maximize the likelihood of p of x parameterized by theta. So at the end, currently we are just interested in finding those theta, the theta max,
Mm-hmm.
this theta k plus 1, which is going to end up at maximum, that is going to maximize our likelihood of p of x.
Okay.
So so this theta k of k plus 1 and sorry, em algorithm generally converges to a local minimum. It might also sometimes end up at a critical point, not like a saddle point or anything. Uh, Saddle point or something similar to how gradient descent. Yes, similar to gradient descent, but yeah. So,
Okay.
but in here we are, So in M step, we are maximizing over theta, and we are just interested in finding this local, yeah, local maximum value of theta k plus one that gives us a local maximum of p of x. And but is E and M step, yeah. So I just want to ensure that it's nailed down and you are able to intuitively visualize why this is making sense and how it flows. Uh, First, consider a family of different distributions. Choose one simple distribution, and then for that distribution, for that L, you change this theta, and then you move to the mode of that distribution. Then the new theta, you again get you again keep that theta as constant. Again, consider a family of distributions. Then you would get a new distribution, and slowly and steadily you would move your theta in such a way that would maximize p of x.
Okay, got it.
Okay, so I'm hoping Jash and Deep, you don't have any questions. So, that's our E and M step basically. And now, so one thing I wanted to mention is this Q. Now, because we have considered T as a discrete random variable, this Q is simply yeah. So Q of Ti is equals to, say, simply we need to just ensure this constraint, and we would have uh, if yeah, and we would have C different parameters like compared to, if we are comparing it to GMM, then each of this would be pi 1, pi 2, pi 3 till pi C, and you need just to ensure this would sum to 1. So, but in essence, if let's say if T is a continuous random variable, then Q of Ti is equals to C is not just some collection of parameters, but it's actually a proper probability distribution. And this each step in such cases, what we are essentially doing is not so it's yeah. So this is called like a functional calculus. Now, instead of optimizing over a single I've been saying Q as a parameter, but in essence Q is not a parameter, Q is some function, and we are moving a functional space, and we are choosing different functions and choosing the best function. So each of this each of this Q1 is denoting some function, a probability distribution. Q of Ti is equals to C, and then we are moving through this functional space, and so theta is properly a parameter. It would be a 1D or ND parameters, but Q is not some in case of, so here you can say you can treat it as a C dimensional parameter. But if you are going in continuous random variable, if the T is not a discrete random variable but T is continuous, then instead the constraint would be Q of Ti needs to be just integrated to 1, and then Q of Ti would be a PDF. And then essentially, so yeah, so there is a whole branch of mathematics that deals with functional derivatives. So entire mathematics that calculus that we saw is just dealing with parameters and moving in the parameter space, where each of these theta is a scalar or a vector, and just moving through that gradient descent and all of the optimization algorithms. But this is like yeah, if T is a continuous random variable, then this all becomes like you need to calculate this functional derivatives. Okay, now I have this function, and if I move the function around, so yeah, this is very counterintuitive, all of this. But yeah, so moving a function around, how it's changing this my likelihood. So I think Jay, you had asked some question about where we would optimize over functions and consider different functions previously. So if T would be a continuous variable, and you would want to maximize this through proper mathematical steps, the you can just like plug this into some functional calculus formula, and then you can get your best function Q. This function Q would be obviously a PDF uh, density function, because we need to ensure this constraint. But yeah, so in essence, in this Q is, I have been calling it as a parameter, but it's essentially a PDF. In discrete case, it's PMF, and then that's why we can also just call it a vector with this constraint. So simply in each step, expectation step of expectation maximization, we would find this distribution Q of k plus 1. Yeah, this indicates that I've kept theta as a constant. Theta is equals to theta k. And in M step, we would keep Q as a constant. Yeah. this is what we are doing in expectation maximization. These are our two objectives. First, increase the lower bound to a good enough q, and then for that q, increase the theta, and then iteratively do each step m step, each step m step. So yeah, I hope you don't have any doubts in this. And then now in expectation step, so showing this lower bound, uh, where, yeah, so this is where we introduce this lower bound. First introduce this free parameter q of ti, and then introduce lower bound by using Jensen's inequality. We can also kind of like this is just another way, and this isn't like this proof is from like this Chuck. So this is more of an easier proof. So this is summation over t is this latent variable, just using this marginalization principle. And then we are introducing so L of q theta. Let's just introduce this some function, some value. So here, like in Bishop, the common notation is z is latent variable. I would just like, so it's like I'm interchangeably using z and t. In most of the textbooks, you would see using z. Z is the generally the common name convention for the latent variable. So let's just this be some L of q theta that we have just defined, and KL divergence between q and p. You know, here p is posterior, so given your x, yeah, so p of t given x. So given your x, the probability of the latent variable. Probability of z given x. Like all of this is just parameterized by theta, so I'm just skipping theta. But just remember, theta is kind of hidden in all of these places because we are in essence optimizing over theta. So this is just like definition of KL divergence, and so let's just add both of these L of q theta. And here this LQ theta is just like it's a lower bound, and we are proving this lower bound is always less than p of x. So if we just add both of these values, then we would have summation of z q of z log of p of x comma z by qz minus log of and then this thing would simply become summation of z qz by property of logarithm p of x comma z qz times qz p of z given x. This and this thing gets cancelled. And yeah, even you can write this as probability of z given x times probability of x. the probability of z given x also cancels, and then you are just left with probability of x. So this thing becomes then, since log of p of x is independent of z, you can just take that out. And then this thing just sums up to 1. So simply our log likelihood that we are interested in is just the summation of this and this. Just remember p is a posterior p of z given x. Yeah. So now we know this thing is always going to be positive, and hence yeah. So this simply becomes, then we have this log, our log likelihood. So yeah. So this p of x, log p of x, we know it's the same thing, optimizing over p of x or optimizing over log of p of x. And evidence lower bound is over lower bound of log likelihood. So this thing just evaluates to n because KL is always negative. So I think we have yeah and like seeing it in this way helps us like I'll just stop here because we are running out of time. uh, so if this equation will help us in like optimizing over L of Q of theta in E step and M step, and in so you will see that okay, since E step is just we are not going to learn functional calculus and see how to optimize Q, because we can write it in this form, and we know that Q maximum over Q is just when Q is equals to P. So we would see to, in next lecture that our E step would just yield that we just need to equate Q to the posterior P. So it's simply like if you are doing so if we are maximizing Q over this, then so, hmm, not maximizing, sorry, minimizing. If we are changing our distributions Q, now you can see that this is going to be we are like optimizing over different distributions, considering different distributions, and the minimum value is going to be hit when Q is equals to P. That's what basically E step would come out to be, and then M step would be yeah, since M step is parameter, we can just use gradient descent or any of our normal optimization algorithms for M step. And yeah, we'll see all of this in next lecture. But any doubts in failure, like even any doubts in past lecture, I'm going to stop here. Like in next lecture, we'll go through individually E step and M step uh, in more detail. So like in both of these steps, we are going to just like work with these two equations, but like substituting this L of theta, yeah, LQ theta that we found here, substituting here, how the math comes out to be. And then we would see some, yeah, then we would again see GMM with respect to, and then yeah, in next lecture, would also go through how these formulas in GMM came to be using EM algorithm. And if time permits, we would also visit key means through the scope of EM algorithm. Yeah, any doubts till here? Were you able to understand? Can anyone provide a summary if possible? Any feedback? Should I need to go faster? Should I need to go slower? Nothing.
I think in terms of feedback, it was really good. So thank you.
Sure. Thanks. No problem.
And I think in terms of the pace, that's perfect. So I think you don't need to like go faster or slower. I think that's fine.
That's nice. So if nothing else, maybe should we stop here?
I've got one question in one of the equation. I think, can you scroll up? I
Yep.
I think it's
Just tell me where to stop.
yeah, keep scrolling up. I think it was just, yeah, I think it's here. It's
Mhm.
just for when you introduce all the family of lower bound.
Mhm.
So I think it's
So I introduced like family of lower bounds over here.
yeah, okay, yeah, scroll up.
Hmm.
Yeah, stop. Yeah, there. Right.
Yeah.
Okay. So we are trying to maximize the likelihood, right? So we got this theta given x,
Hmm.
and then where do we get this from? When
This
we
part.
yeah, this part.
Yeah. So it's a definition of likelihood, right? So like so if I've given you a bunch of data points x, then the likelihood simply says that okay, what is a like I'll fix this parameters theta, and then for this parameters what's the likelihood of seeing that data. So we would just multiply each. So now let's say p of theta is some, again, let's say this normal distribution. Then what I would do in that case is plug in all of these, uh, plug in my value of nu and sigma, and then say okay, what is the probability that this x data point came from this normal, and then just multiply all the data points that I have shown, because this comes from the IID assumption. And then if I multiply all of these data points, and then I would change my nu and sigma in such a way that I would get this maximum product of one of them. So if in review 2, I think we did this maximum likelihood estimate. And yeah, and likelihood of you seeing your data is just a probability of over your parameters theta. What's the probability? Your j is your theta, and we just multiply all of these x is equals to xi together. So does that answer? So if x is equals to xi was if we assume that probability of x is equal to xi is a normal distribution, then we would just fix some value of nu and sigma, just multiply the probability of seeing each of these data points, and then change nu and sigma in such a way that would, so like this was something I even indicated that if the thing that it would come out to be is just your definition of nu and sigma in that case, if I've given you a bunch of data points. Yeah, this this is
Yeah,
the
that makes sense. Okay.
yeah. Any more doubts?
Yeah, that makes sense. Thank you.
Sure. So yeah, maybe we can stop it here. And today it was nice talking to you. And yeah, if you face like if you're revisiting anything, if you face any doubts, then just feel free to ping on Discord. Yeah, Swapnil, I think we are good to go for today.